Hi, my name is Vishnu Manoj, and welcome to this short introduction to linear programming. So, let's say you're trying to start a business and you were trying to sell tables and chairs that you handcrafted yourself, right? Now, the goal to any business is maximizing your profits. But since you're handcrafting these tables and chairs, there's obviously going to be some limits on the amount of money you can spend and the time you can commit to your business. So the question is, how do you maximize your profits while meeting your limitations at the same time? Mathematically, you can use linear programming. So the formal definition of a linear programming problem is basically maximizing or minimizing a certain objective function z, and this objective function will be subject to restrictions that are often expressed in the form of linear inequalities. So in the case of our furniture example, the profit is our objective function, and the limitations of the time and money is basically our restrictions. So this is all great, but how do we solve a linear programming problem? Now there are two ways we can go about this. The first method is very intuitive, popularly known as the graphical method. So let's try to solve this linear programming problem where you had to maximize this function and you have these constraints. So our first step is basically graphing the constraints and finding the common region that satisfies all these inequalities. This region is also known as the feasible region, right? Now, these contain all the points that satisfy these inequalities, but we don't want just any input. We want the input that maximizes this function. So in order to find that, we look for what is known as extreme points. These points are at the intersection of inequalities. So in our case, we have 0, 4, 1.5, 2.5, 3, 0, and our origin, right? Now, once you find these extreme points, all you have to do is plug them in and see which one gives the maximum value, which in our case is going to be 1.5, 2.5, and the maximum value we obtain is 430. Pretty simple, right? But as intuitive as it is, this method also has its drawbacks. Let's say you had 1,000 extreme points, right? Unless you have all the time in the world, plugging in everything is going to take a long, long time. And secondly, we only had two variables in this linear programming problem, right? It's also it's possible that we may have 3, 4, 5 variables. And so if you wanted to use the graphical method, you would have to require a multi-dimensional plane. And so as the number of variables increase, it becomes less and less intuitive for obvious reasons. So even though graphical method is very simple and intuitive, we can actually come up with a general idea, a more general approach to solving linear programming problems. This is where the simplex method comes in. In this method, we are repeatedly forming a set of operations to find our extreme point that actually maximizes or minimizes our certain objective function. This method was actually introduced by the same guy who formally introduced the concept of linear programming, George V. Dantzig. Now, his approach was leaning more towards linear algebra. So let's try to solve the same problem that we did before for the graphical method, right? Now, as I stated earlier, his approach was more towards linear algebra, which requires a linear system of equations. Now, we have inequalities here, though. How do we represent those in the form of linear equations? To do this, we introduce what is known as slack variables to each of these inequalities. So in this case, we have two inequalities, 2x plus 2y less than or equal to 8, 5x plus 3y less than or equal to 5, and you add slack variables to each of these inequalities to get these two equations. Now, one other equation that we require to form our linear system is our objective function. So the idea is to basically take everything to one side and you get this equation. The first two rows of the table that is formed here represent our inequalities, our constraints, and the last row, also known as the objective row, represents our objective function. Now you're going to have to remember this this row, because we're going to visit this quite often. Apologies for that. So the next step is finding the pivot for the variable that influences the objective function the most. Now, let's try to pull the objective function from the objective row, which in our first iteration is going to return our same objective function, right? Now, x has the largest coefficient here. So clearly, if you have any small change in x, it can significantly change the overall output of z, right? So clearly, x is the variable that influences the function the most. Now you mark this column as the pivotal column. You can also select the pivotal column by looking for the most negative entry in the objective row. Now, since we decided that we're going to fix a value for x first, we can't just fix any value for it. We need to find a value that satisfies both these constraints as well. Now, in order to do that, we select a pivotal row. To do this, we divide every row in the constant column with the elements in the same row of the pivotal column. And we select the row that gives the smaller quotient. So in this case, we divide 8 over 2 and we get 4. We divide 15 over 5 and we get 3. Now 3 is obviously the smaller of the two, so we mark this row as the pivotal row. The intersection of the pivotal column and the pivotal row is what gives the pivot. Our next step is pivoting, which is basically linear algebra, where you convert the pivot to 1 and everything above and below the pivot to 0. This can be done by using simple row operations, which I wouldn't get to in this video. Now, at the end of this iteration, we run what is known as the optimality test, which is basically going through the objective row to check if we have any negative entries whatsoever. In our case, we have negative 28. So this means we are not done yet. We need to do one more iteration. So we stop repeating the previous set of operations if there are no negative entries in the objective row. So let's say you generated this final table after repeating the previous set of steps for the variable y. Now you have no negative entries here, but why exactly do we stop there? If you try to pull the objective function from the objective row here, you get this. It is very obvious that z becomes gets the maximum value if u and v are both 0, right? And you got to remember, our objective function did not have the variables u and v. U and v were just slack variables that we introduced to our inequalities. So if you wanted to solve the system now, you can completely ignore these columns and solve the rest of the system to find your solution. So in our case, y will be 5 over 2, x will be 3 over 2, and z, which is the maximum value that you obtain, is going to be 430, which is the exact same solution that we obtained for our graphical method. So this is all great, but where exactly can you apply linear programming? Is it just for making a business for selling furniture? Well, studies show that you can actually apply this anywhere. If you really think about it, you can actually think of any problem and bring it down to the form of linear equations or inequalities. Now with that, as you've just seen, we can solve a linear programming problem and maximize whatever you want to maximize. So yeah, that is the end of this presentation. I hope you enjoyed it. Thank you so much.